Okay, so I'll tell you about Green's theorem for today, which is one of the big three theorems in multivariable calculus, the other two being Stokes and Gauss's divergence theorem, which actually can be regarded as a generalization of Green's theorem. And really, the way you should think about this for now is as a useful tool to understand when a vector field is conservative. So remember, so far we're trying to understand this problem about conservative vector fields. A vector field being conservative remember, so you had a force field, and let's say this was conservative. What that meant is that if you take any two arbitrary points, P and Q, and you choose different trajectories connecting these 2 points, so maybe you choose one trajectory, which is this one, and you choose a different trajectory, which is that one, right? Then the W, the work done by the force field along any of these curves or trajectories, right? Remember, the force field may look something like this. Right, so remember the condition of being conservative was that W, the work, is independent of trajectory. Of the path chosen between P and Q. And so we have been interested in understanding when can we guarantee that a vector field is conservative. This is like a very special property. It's not a property that you would expect to see to hold just for an arbitrary vector field. And so the question that we have been trying to understand is, this is the main question to a large extent for the remaining part of this class, is when is F conservative? And we already have some partial answers, right, to this question. So let's just write it here. So some partial answer, right, was that if F is if F admits a potential function, right, if F is the gradient of some scalar field, right, then F is conservative. Okay? And we knew that in this case the work was just the difference in the potential between Q and P. And so what I want to discuss today is another partial answer, which actually ends up being equivalent to being conservative, but Green's theorem will give us a way to quantify the failure of this condition to happen. Okay, so this is the first partial answer, right? Here's a second answer. If the work done along any closed curve is 0, then F is conservative. Let me just write it like So let's think about what this statement means for a second. What I'm saying is imagine that you have a curve, what's sometimes also called a closed loop. Maybe that's a tautology, but imagine you just have a curve. You choose a point, and now you just choose a path from this point to itself. So choose like your favorite curve. It can do whatever crazy stuff it wants. But in the end, right, so here there's like, it's sort of knotted in a way. But so you, it can be like a complicated curve. But the point is that it, like the initial and final endpoints are the same. So P is equal to Q. That's what I'm trying to say. And so the statement is imagine that the work along this curve is 0. And not only along this curve, but imagine that you also choose another curve, closed loop. Maybe one that does this. Right? There's another closed loop there. Imagine that that work is also 0, and imagine that the work is always 0 for any of these closed loops that I'm drawing. So the statement is, if this condition holds, then the vector field has to be conservative. And so let's see why is 2 true. So we want to check that if you satisfy this, then the vector field is conservative, meaning that the work is independent of the trajectory. Well, here's a trick. Again, let's just draw one more time that picture. Okay, I realized the explanation I was giving was a bit too complicated. So again, I'm trying to explain why is 2 true. So 2 was just a statement that if the work is 0 along any closed loop, then the vector field is conservative. So again, the statement of the vector field being conservative is that if you choose 2 points, PQ, and you take 2 curves, C1 and C2, then the work along C1 has to be the same as the work along C2, right? And so how can we see that under the assumption that the work is always 0 along any closed loop? Well, the observation is that you start at a P and you go to Q. You can go to Q through path C1, and then you want to come back to P, but rather than going back along C1 again, or minus or the opposite orientation, you can do P to Q through C1, and then you go back through C2, right? Strictly speaking, you're not going through C2, you're going through C2 with the opposite orientation, meaning that you're reversing the velocity that your velocity to travel along C2. And so usually the way in which you would say that is that C1 plus minus C2, right? That means concatenate the 2 curves. So take the curve C1 and concatenate it with the curve C2, but with the reverse orientation, so that this is really, you can really join them together. So now you're changing orientations. Well, so the statement is that that has to be a closed curve, right? And so by the property 2, so by 2, the assumption is that the work is always 0 along any closed curve, and so the work along the curve C1 plus minus C2 has to be 0. But there's something that maybe it was clear, but if not, let me just mention it right now, is that work is additive, meaning that if you want to compute the work, and I think we have used that implicitly, meaning that if you want to compute the work along these two curves, you can just, along this closed curve, you can just compute the work here and add it to the work here. So in other words, what I'm saying is that the work along C2 plus the work along minus C2 has to be 0. Okay? But now, how is this work? This is the work along the same curve as C2, but with the opposite orientation. So that means that if you're driving with a car, and you have certain velocity as you're driving this car, for the opposite orientation, you're just switching the directions of your of motion. So you're just reversing the velocity that you're using for traveling along this path. And so what I'm trying to say is that since you're switching velocities, the work along this curve is really minus the work along the curve C2, because you flip the sign of the velocity. So you flip the velocity. And so that means that the work along the curve C1 minus the work along the curve C2 has to be 0. Or in other words, the work along the curve C1 has to be the same as the work along the curve C2. Okay? So what this is saying is that work 0 along closed loops implies that the vector field is conservative. And actually, if you, well, now that I'm being recorded, you can do this. Like, if you run this movie backwards, literally, you can show that if the work is conservative, if the vector field is conservative, then the work along any closed loop must be 0. So, conversely, so let me just write it here. So let me say it. 0 work along any closed curve implies that f is conservative. And conversely, if f is conservative, then it's, again, running this argument backwards, it's not difficult to see that that indeed the work must be 0 along. Let me just write it like this. Work along any closed curve is 0, implies f is conservative. And so, and if f is conservative, then the work along any closed curve is 0. So when you think about conservative vector fields, you can just think of them as fields whose work is 0 along closed curves. So what that means is that if f is not conservative, so it's not conservative, then you can find a loop, then you can find a closed loop where what happens? Well, you can find a closed loop where the work along this curve is non-zero, right? That's the point of not 0. And the content of Green's theorem is that it will allow us to so let me just say it like this: the work along the curve C is not 0. And the point of Green's theorem is that it will give us a way to compute this work. I mean, you can always compute this work using the integral, right? You can integrate the dot product of the force with the velocity. But the Green's theorem will give us will give us a new way to find w in terms of a double integral, which is an interesting thing. So in the next video, I'll explain to you what this double integral is and what do you need to put inside the integral to get the work. And so we'll see that actually this it will start giving us like a useful characterization to detect whether a vector field is conservative or not.